So welcome to mathematics class, and now we are going to learn about surface area and volumes. So let us see what are the topics to be covered. So initially we will learn all kinds of surface areas, like we will learn surface area of a cuboid and a cube, then surface area of a right circular cylinder, then of a right circular cone, then of a sphere. And after that, after covering the surface areas, we will go for volumes: volume of a cuboid, volume of a cylinder, volume of a right circular cone, and finally volume of a sphere. So let us start off with the surface area of a cuboid and a cube. So before we begin to talk about the surface areas of cuboids and cubes, let us see how did all these two-dimensional and three-dimensional come into place. It all started with a zero-dimension point, and now if we extend this point in one dimension along the length, we get a line. A line has only one dimension, right? From zero-dimension point, we have now obtained a one-dimensional figure which has only length. Now if we extend this line in two-dimensional manner, or we extend this line according to the breadth, we get a two-dimensional figure, right? And here we have obtained a rectangle, right? Now to get 3D figures, we have to extend two-dimensional figures further, and if we extend these two-dimensional figures along the height or the depth, we get what is called the three-dimensional figures. The objects which we can see in our daily life are mainly three-dimensional figures, right? They all have certain length, certain breadth, and certain height. So this is how we can classify three-dimensional figures, and how we have obtained three-dimensional figures from two-dimensional figures and so on, starting from a zero-dimensional point. I think you have got the entire concept. So let us learn about cuboid. I think you all know about what is a cuboid, right? It is just a solid kind of rectangle. It is, all the faces are rectangles, right? Or all the lengths of the height, breadth, length, all are different from each other, right? So such kind of solid figures are called as cuboid. Now let us see how can we build a cuboid. Let us start building a cuboid. And by building a cuboid, actually by building the cuboid from scratch, we will get to know how to find out the surface area of that cuboid effectively. So let us start off by building the base. The base, you can see, it is considered it that this plane is into the screen. This is the page which has been cut out. This is the sheet, and this has been laid down in such a manner in a horizontal plane. The sheet is resting on a horizontal plane which is directed into the screen. Now to get the sides, what we do, we attach two more sheets here, right? Or we have attached two more sheets, like as you can see here. Two more sheets has been attached to the side of the base and has been folded accordingly, right? Now to get the other two sides, this side and this side, we attach two more sides here and here, right? And accordingly fold it. What we have done, we have got a base. We had got the two side faces of the cuboid, and we folded it. The front face and the back face was also folded, right? And this was the cardboard piece or the sheet which we are folding, right? Now for the top, we take a piece which is similar to the base and we place it on top of the cuboid, right? It was open at the top, now we have closed it, and this is actually the top, right? After we have folded this portion, which is this side, after we have folded this portion, if we further fold it, it will cover the top, right? If we have folded one part of it, it is vertical, and if we fold the other part of it even further, it will cover the top. So if we open a cuboid, it will actually look like this, right? And I think you might have seen the cutouts of dice, right? For playing different board games, there are many times the games come with the cutouts of cuboids, right? And those cuboids are actually the dice, right? This is the shape of those dice, right, when you cut it out. So let us call the sides as the breadth is B, the length we take as L, and the height we take as H. Let us assume the values for this as B, L and H. So for this face, which is suppose this one, right? This face was the bottom one. So this is the base and this is the height, right? So this one is the height. And for the back portion also, it is the same. For the top portion, which is this one side is the length, which is this one, this is the length, and the other side is the base, which is this one, right? And this portion is similar to this one, so the dimensions are same. This one is the breadth, this one is the length, and this is the height, right? This one is the height of this face, this side is the height of this face, and accordingly you can label all the other measures of the side. And here we have an image showing all the measures of the side labeled, right? When we have opened the cuboid, all the labels we mention it, and each portion, each rectangular portion we have numbered 1, 2, 3, 4, 5 and 6. All the faces we have numbered. Now for a cuboid, you can see for a cuboid, these were actually the surfaces, right? For the cuboid, these were the surfaces. So if we find out the areas for all these surfaces, we can find out the surface area of the cuboid. So let us try to find out the area of each part and then we will add them up. So for part 1, area is length into h, right? L into h. For part 2, we have area as L into B, right? This part. For the third part, this one, we have area as h into L, right? So you can see that we have got two parts with the same area, h and L till now. Area of the fourth part, this part, is L into B, right? L into B, area of the fourth part. So we have got two L and B also. Area of the fifth part, this one, is B into H, and area of the sixth part is also the same, B into H, right? So you can see we have got all the terms twice, height into length, length into breadth, and base and breadth into height, right? So we have got all these terms twice. So if we add them up, we will get twice of HL plus twice of LB plus twice of BH, right? If we add them all up. And if we add all the areas of these surfaces, we get the surface area of the cuboid. So surface area of a cuboid can be defined as twice of length into breadth plus breadth into height plus height into length, right? This is the surface area of a cuboid. Or you can say, to find out the surface area, if the dimensions are given, length, breadth and height are given, then you can multiply two terms together. You can multiply two terms together, and how many will you get? How many multiplications will you get? Length into breadth, breadth into height and length into height, right? You multiply two terms at a time and add them all up, so you get this term, and then you multiply it with 2 to get the total surface area of a cuboid. And it is as simple as that. So remember the formula for a cuboid. It is length into breadth plus breadth into height plus height into length, and you know how it has come, right? So let us use this to solve a very simple question. Find the surface area of a cuboid whose length, breadth and height are 15 centimeters, 10 centimeters and 20 centimeters respectively. So we are given the dimensions of a cuboid. So what we do, we directly put the values in our obtained formula. So you can see we have multiplied two terms at a time, 15 centimeter into 10 centimeter. First we have multiplied them. Then we have multiplied 10 centimeter into 20 centimeter. Then we have finally multiplied 15 centimeters with 20 centimeters, right? So you can see after multiplying two terms at a time, we don't have any more terms left to be multiplied. And now what we do? We add them all up. We add these all up and then multiply it with 2. This gives us the total surface area of a cuboid. So after finding out what these multiplications give us, we end up with the value of 1300. Now be careful of the unit. It is centimeter square. Areas always have square units. Why? Because areas are obtained by multiplying two lengths, right? We multiply either length into breadth or breadth into height or height into length, right? We are multiplying two things which have the dimensions of length, right? So cm or centimeters times centimeters gives us centimeter square, right? Centimeters times centimeter gives us centimeter square. So you should always keep in mind to write the units after you have obtained the answer, because without the units your answer will always be incomplete. So here you can see, by finding out everything in centimeters, we have obtained the answer in centimeter squared. If we had done the calculations in any other units, we would have got the answer in that unit squared. So you can see surface area is always measured in square units. Now let us try to find out the surface area of a cube with side A. Now cube is a special case of a cuboid, right, where all the sides are of equal length. Cube is nothing but a cuboid with all sides of equal length. So to find the surface area, we take all the length, breadth and height as A, right, of the same length, which is A. So we multiply length into breadth plus breadth into height plus height into length, right? As all of them are A, we just put A in the place of every variable. And finally, when you find out the summation, you get the answer as 6A square, or you can tell the surface area of a cube is 6A square. Now we can interpret this answer in other ways also, like if we have a cube, like we had done in the case of a cuboid, if we had started building the cube, we would have got a shape like this, right? This was the top, this was the base, and these were all the sides, right? Now, as all the sides are A, the areas of all the faces will be the same, A squared, right? Now you can see it has 6 faces. You can see it has 6 faces, so the surface area will always be 6A squared, right? So from here we have also obtained an information that both cube and cuboids have 6 faces, right? 2 as the top and the bottom, and 4 faces on the 4 sides. So from here we get surface area of a cube is 6A square, right? So let us move to the next topic, surface area of a right circular cylinder. Now what is a right circular cylinder? We only know about cylinders which have circular top and bottom, right? So what is a right circular cylinder? Actually, right circular cylinders are those which are erect, or the height of the cylinder actually makes right angles with the base, right? Like if you have a cylinder which goes curved, like in the case of handles of mug, right? The handles of mug are cylindrical, yet they are curved, right? So that kind of curved cylinder is not called right circular cylinder. Right circular cylinders are straight and erect. So how are they formed? Let us start with the base once again. So we take a circular base, then we stack upon similar bases one upon the other to build an erect structure. And this figure, the entire figure, is actually called a right circular cylinder, right? You can see that the cylinder, the height of the cylinder is actually making right angles with the base, right? It is straight and erect, and it can be formed in other ways also. Like, let us take a thin sheet where we have the breadth as H and the length as L, right? We have taken a thin cardboard sheet or of a thin sheet of any material, then of the length L and breadth H, or the height H, whatever you call it. So if we wrap it around, we will end up with a cylinder once again, right? And the height will be H, right? The height of the cylinder will be H because we had wrapped it in this fashion, right? We have just wrapped it and we have not changed the height. So height of the cylinder will still be H, and you can see this curved length, the length or the circumference of the circle of the upper face is actually the entire length, right? As we had wrapped it, the entire length of the top circular face is actually the length of the cardboard sheet we had taken. And as it has formed a circle, now we can also have a radius, right? We can easily measure its radius, we can find its center and easily measure its radius. Now if you try to find out the curved surface area is the area of this curved face, The area of the curved face, as you can see, it is just the same as that of the sheet of cardboard, right? It is the same as this area. So the area is nothing but length into height, right? It is nothing but length into height, area of the cardboard sheet. But what is the length in terms of radius? The length is actually the entire circumference, right? And if the length is the entire circumference, L must also be equal to 2 pi r, right? The circumference of a circle. So here we have replaced L with 2 pi r to get the curved surface area of a cylinder entirely in the terms of radius and the height of the cylinder, which is 2 pi r into h, right? So I think you have got how we find out the curved surface area of a cylinder, and you can find it out by going backwards also. You can cut this cylinder open and it will flatten out as a rectangular sheet, right? And you can find out the length, and the length is nothing but the entire perimeter of the circle because you had opened it, right? And the height will be the same as that of the height of cylinder itself. So you get the curved surface area as the height into the entire length, which is perimeter of the circle 2 pi r. So keep in mind this basic formula for the curved surface area of a right circular cylinder. Now, till now we have found out the curved surface area of a cylinder, but we had not considered the top and the bottom, right? Because we had only considered the curved surface. Now, if we consider a closed cylinder, or we also have a top surface area and a bottom surface area, right? If we also have a top surface and a bottom surface along with the curved surface, we know that the curved surface area of a cylinder is 2 pi r h, right? 2 pi r into h. And now in addition to that, we have two circular faces at the top and the bottom, and the area of the circular faces is obviously pi r square, right? Because they had radius r, so their areas will be pi r square. So area of the top is pi r square, area of the circular face, and for the base also the area is same, pi r square. So curved surface area of a cylinder, we know 2 pi r h, and if we add these two areas with this curved surface area, we will get the entire surface area or the total surface area of this closed cylinder. So we get the total surface area of a cylinder as 2 pi r h, the curved surface area, and pi r square plus pi r square, which is 2 pi r square. Now we take 2 pi r common, 2 pi r into r plus h. So we get the total surface area of a cylinder as 2 pi r into r plus h, right? So this is the total surface area of a cylinder. Now either you can use this formula for finding out the total surface area of a closed cylinder, or it is better to find out the curved surface area separately and then add them with the top surface area and the bottom surface area. Because if you even forget this formula, you will always get the right answer by going step by step from the initial process, right? You can remember the curved surface area is nothing but 2 pi r into the height. Then you can find out the surface area for the top and the bottom, both of which is pi r square. Add them up, 2 pi r h plus 2 pi r square, and there you will get the area or the total surface area for a closed right circular cylinder. So let us solve one more question based on this. The inner diameter of a circular well is 3.5 meters. It is 10 meter deep. Or we have a well which is 3.5 meter in radius. The radius of the well is 3.5 meters, and the depth, or if we can consider it as a cylinder, we can consider the depth as the height also, right? The depth is the depth will measure the same as the height of the well. So we know the radius and the height of the well, or the depth of the well. So we are asked to find out the inner curved surface area and the cost of plastering this curved surface at the rate of rupees 40 per meter square. So let us do it step by step. So let us find out the inner curved surface area. Now the inside surface is the surface of a cylinder, right? It is nothing but the curved surface of a cylinder. Mind it, the well is not covered. The well is not covered, and what is asked is inner curved surface area, not even the area of the base, because it is flat, right? We are not asked to find the flat surface areas, but the curved surface area. So inner curved surface area will be the surface area for the cylinder, right? The curved surface area for a cylinder, which is 2 pi RH. So by putting the value of the radius, which is 3.5 meters, and the height 10 meters, and the specific units meter square, we get the answer as 219.8 meter square, right? So this is the inner curved surface of the inner curved surface area of the well, right? So let us find out the cost of plastering the curved surface. Now if the cost is rupees 40 per meter square for plastering, and we have 219.8 meter squares of area, so our cost will be rupees 40 multiplied with 219.8. Why? Because the cost for plastering 1 meter square is 40, so the cost of plastering 219.8 meters will be 40 into 219.8, right? 40 times the area. So we get the cost of plastering as rupees 40 into the curved surface area, and the answer comes out to be rupees 8,792. This is the cost of plastering the curved surface at the rate of rupees 40 per meter square. Now be careful, many make mistakes here, like rupees 40, and here mistakenly sometimes we write meter square, because this is the area, right? Sometimes we write meter square here, but can cost be rupees and meter square at the same time? It cannot be, right? So we should not write meter square when we are multiplying the area with the cost, right? So when we are finding out the cost, we should just write the area which we have got. We should not write the units with it, because we already have one unit, which is the rupees, and cost always comes out in rupees, right? You cannot have the cost as something meter square. So keep these mistakes in mind, and I hope you will not commit such mistakes in exams. So let us move forward. Okay, now let us talk about the right circular cone. Now how is it formed? Again, we draw a straight line, and we take a small triangular cardboard, a right triangular cardboard, right? Because we are trying to obtain a right circular cone, and therefore we are taking a right triangle, and along the axis of AB, what we are doing, we are making it rotate, and by this we are actually getting right triangles at all the sides, at all the places, right? And if we look at the summation of all these right triangles over all the spaces which is around the axis AB, it comes out to be a cylinder, not a cylinder, sorry, it comes out to be a cone, right? If we are rotating a right triangle along the axis, you can see along the axis AB, if we are rotating that right triangle, we are actually getting a right circular cone. Or you can see that the cone, one part of the cone, if you slice a cone at one part, you will see that the cross section is that of a right triangle. So there is one more way to obtain a cone. Let us not try to build the cone by that method. Rather, we will try to cut the cone and see it backwards, how we can obtain cone from a certain kind of figure. So let us make a cut vertically. Then we repeat a part. Here we have the edges A and B. And if we flatten it out, you will see that it is a kind of circular in nature with one sector missing. This sector is missing, right? And that means the surface area of a right circular cone will be a certain fraction of that of a circle, right? It should be it should have something in relation to the surface area or the area of a circle. So now let us find out this by taking this part into consideration, because finding area using this flat portion is very easy. So what we do here, we divide this into very small triangles. You can see we take B1, B2, B3 and so on with all the vertices on this circle, and we join this to form small triangles. You can see here one small triangle, here is one more small triangle, and so on. There are infinitely many small triangles, right? We are just assuming they are small enough so that we can consider their length. So what is the area for such triangles? Area of each triangle will be half into the base into the height, right? And what is the height here? The height is the radius, right? The height is the radius. Now wait a minute. This thing cannot be a triangle, right? Because this line is a circle. These lines are of a circle, so it is curved. How can we call it a triangle? Now, when you are making a circle, a part of the circle smaller and smaller and smaller, it seems like that it is becoming a small line segment. If you try to remove a very small portion out of the circle, it seems as if it is a straight line. Like if we have a curved surface and we are taking out this much small portion, the small portion will of course seem like a small line segment, right? If we take out this portion, it will almost look like this, a small line segment. So we are assuming that these portions are so small that we can consider them as small line segments. So we can consider these small parts as triangles. So the bases are the lengths of the bases B1, B2, B3 and so on, and the height is nothing but the radius, which is L. So the area of the entire piece, this entire thing, is sum of areas of all the triangles, or half into B1 into L, half into B2 into L, half into B3 into L, and so on, right? Half into the base height, the base and the height, half into base and the height. So if we take out the length common, and half common, we will get half into length times B1 plus B2 plus B3 and so on, right? It will end up, after going from B, it will start from B and all the length will end up till A, right? and we are adding this lengths up, right? We are adding all these lengths, b1, b2, b3 and so on, right? We are adding all these lengths up, and if we add all these lengths, what will we get? This plus this plus this plus this plus this plus this and so on. Aren't we getting the length of this major arc AB, right? Because these small portions are actually the parts of the arc AB, and if we are adding the small parts of the arc, we should get the entire arc back. So we finally end up with half into length of the entire curved boundary, which is AB. So here the curved boundary is nothing but 2 pi r, right? The length of the curved boundary, the length of the curved circle is nothing but the perimeter of a circle, which is 2 pi r, right? It is the, if we consider the entire perimeter of the circle, it is 2 pi r. So curved surface area of a cone comes out to be half into length into 2 pi r, and if we find out the answer, the curved surface area comes out to be pi rl. So you can see we can easily find out the curved surface area for a cone with the lateral height. The slant height is called the lateral height, or you can tell it as L. It is named as L because lateral height, and the perpendicular height, you can label it as H, and the radius is labeled as R, right? And here we have a right angle because it is a right circular cone. So curved surface area of a cone we have obtained as pi rl. And how can we obtain L if we don't know the value of L but we know the value of H and R? How can we find out the value of L? Now as R, H and L form a right triangle, we can directly use the Pythagorean theorem, and we will get L as square root of R square plus H square, right? L square will be H square plus R square. So if we take square roots on both sides, we will get L equals to R square square root of R square plus H square. So you can easily find the curved surface area even when you are given the height and the radius. So let's solve one simple question. The height of a cone is 16 centimeters and its base radius is 12 centimeters. And by the height of a cone, we always mean this H. By height, we always mean this H. If you want to specify L by saying height, you have to mention lateral height or slant height. If slant or lateral is not mentioned, the height always means the perpendicular height. So keep this point also in mind. Now the height of the cone is 16 centimeter and base radius is 12 centimeter. So height is given, this H is given as 16 centimeters, R is given as 12 centimeters. Of course, don't forget to write the unit. Okay, so let us find the curved surface area and the total surface area of this cone. Now, but the curved surface area, we all know it is pi rl, right? The curved surface area of the cone. Now, like cylinder, if we are talking about a closed cone, then the area of the top must also be taken into account. And what is the top? The top is nothing but a circle of radius r, right? The top is nothing but a circle of radius r. So the top area, if we add it with pi rl, then we will get the total surface area of the right circular cone, or the closed right circular cone. Closed right circular cone. So here we start with the solution by specifying the given values. H equals 16 centimeter and R equals 12 centimeters. So from Pythagorean theorem we can find out the length of L very easily. L square plus L square equals, or the hypotenuse equals, height square plus radius square. So by taking square roots on both the sides we get square root of 16 square plus 12 square, and if you find it out you will end up with 20 centimeter as the slant height or the lateral height. Now the curved surface area is pi r L, pi r times lateral height. So pi, the value of pi we have taken as 3.14. If you wish you can take as 22 by 7, it doesn't matter. So we have taken 3.14 as pi into radius 12 centimeter into the lateral height 20 centimeter, and the answer unit which we get, the unit which we get is centimeters squared or square centimeters. So we find the curved surface area as 753.6 centimeters squared. So we have found out the curved surface area, and we are left with the total surface area. And so when we are talking about the total surface area, we just need to consider the top and nothing else. So to find out the total surface area of our right circular cone, we add the curved surface area with the surface area of the top, which is nothing but the area of a circle, pi r square. So by putting in the respective values and specifying the correct units, we get the answer as 1205.76 centimeters square. So you can see how we have easily found out the surface area of a closed right circular cone, right? So in this way, either you can find out the surface area of any open solid or just the curved surface, or you can find out the area for closed solid objects also, or the total surface area, just by adding the surface area for the portion from where the object is closed. Here the object has been closed from the top, so we are adding up the surface area for the top, which is nothing but area of a circle. Now let us talk about a sphere. Now how is a sphere formed? Let us take a circle, because circle is such a figure which we can draw easily. It is just a round shape, right? We can draw it easily with a compass. So let us start with a very simple shape to get a simple round shape called sphere. And when you spin this circle around its axis or around its diameter, when you spin this circle around its diameter, you obtain a sphere, right? When you are spinning this circle, around very fast, you will notice that it is forming the shape of a sphere, right? The high speed in which it is rotating, your eyes will see that high speed as a sphere. So sphere is nothing but a 3D object whose two-dimensional figure is a circle, right? So let us find out what is the surface area. Now finding the surface area of a sphere is not that easy as we had done for all the figures which we had considered till now. For this you actually need a sphere and a long piece of string. And now what we do, we have put a needle on top of the sphere for support of the string. Now what we do, we keep on wrapping the string around and around. We keep on wrapping the string around so that it covers the entire sphere. We wound the string around the sphere to cover it completely. And after winding it, what we do, we cut that string at the point where it ends windings, and then we unwound it. We then unwind it to get these figures. We get circles. If we put them in circular fashions, we get 4 circles of the same radius. And of course, if we get 4 circles of the same radius by the help of the string, then of course the total surface area for this sphere must have been that of the 4 circles, right? It should have been pi r square plus pi r square plus pi r square plus pi r square, right? This should have been the surface area for the sphere. So the surface area of sphere we get as 4 pi r square. So what we had done, we had taken a string and winded it up over the sphere, and then we unwinded it. And then we had put it on a flat plane in shape of circles of the same radius as that of the sphere. If the sphere had radius r, we had kept the string in circular fashions in circles of radius r only. This radius r is the same as that of the sphere. So if we put it in the form of circles, it covers 4 circles. So the surface area of the sphere must have been 4 pi r square, right? Because if it was the areas of 4 circles and the entire string was on the sphere, then both the areas should be same. So we again obtain the surface area of a solid figure. Which is a sphere. So here it is 4 pi r square. So let us use this to solve yet one simple question. Now I know you all love ice cream, right? So let us find out the surface area of an ice cream. This figure looks a bit complicated if you look at it in the point of view of its construction, because you can see the top part is something else and the bottom part is something else, and now we are asking you to find the surface area. So it is not so easy, but actually if you break it down into certain solid figures, it becomes very simple. So find the total surface area of the ice cream cone shown in the figure. The ice cream on the top is hemispherical and the base is a cone, right? Obviously the base should be cone, or why would it be called an ice cream cone? So now you can see the top portion is hemispherical, or it is half of a sphere, and the base is a cone, right? Circular cone. And we are given the lateral height also for the cone and the radius of the hemisphere. Now if the hemisphere and the cone has the same base, the hemisphere also has a circular base, the cone also has a circular base which is attached, right? It is directly attached on top of each other. So both of them must have the same radius, as they have the same circular faces. So both of them must have the same radius also. So here we have the radius of the hemisphere also as 2 centimeter, radius of the cone also we have as 2 centimeters. So let us solve step by step. First let us solve for the topmost part. Surface area of ice cream we get as half into surface area of sphere, right? And why is that? This is because if the full sphere was there, we would have taken the full surface area. Now only we are left with half of the surface. So for hemisphere, the surface area is half into the surface area of a sphere. which is half into 4 pi r square, which is nothing but 2 pi r square. So let us put the values in it, and finally by putting the values we get the surface area of the hemisphere or the top ice cream part as 12.56 centimeter square, right? Because everything we have put the values, every values we have put here, all these are in centimeters. So we have got here the values as 12.56 centimeter square, the surface area of the top ice cream. Now for the bottom portion, which is the cone, the surface area is that of a right circular cone, right? The curved surface area, because the bases are covered. So as the base is not exposed or the base is not at the surface, we cannot consider it for taking it into the surface area, right? So we cannot consider the surface area for the base as it is not at the surface. So we can only consider the surface area for the cone, which is pi rl, the curved surface area, and by putting the values of radius 2 centimeter and the lateral height or the slant height as 5 centimeters, we get the value of the curved surface area as 31.4 centimeter square. And of course in every cases here we have taken pi as 3.14. You are free to take the value as 22/7. So to find the total surface area, what we do, we add the surface area for the hemisphere and the surface area for the cone, right? The lateral surface area or the curved surface area for the cone. So here we have the curved surface area for the hemisphere. Here is the curved surface area for the cone, right? This is the curved surface area for the cone, and now we have here the value for the total surface area, which is 43.9631 centimeter square, right? So this is forget this part, 3.14, this is not the answer. So we have the answer as 43.96 centimeter square. So this is the answer, right? So what we have done here, to find out the surface area of a complicated figure which is consisting of individual 3D objects which we have learned so far, we consider each object individually. So first we had considered the hemisphere, and we had found out the area which is on the surface or which is exposed. The area was nothing but the curved surface area of the sphere, right? So half of curved surface area of the sphere, which is 2 pi r square, we get the surface area of the top hemisphere, right? So surface area for the top we have got. Now for the bottom, what we do, we find the curved surface area of the cone, because the face of the flat face of the cone is yet not exposed, right? It is not on the surface. So surface area for the cone or the curved surface area for the cone we get as pi rl, and therefore after adding these two areas, the top surface area and the bottom surface area, we finally obtain the total surface area of the given object. So you can see how we can easily find out the surface areas for simple figures as well as complicated figures using just the simple concepts of the figures which we have learned so far. So in this class we have learnt about the surface area of a cuboid and a cube, of a right circular cylinder, a right circular cone, and that of a sphere, right? And we now also know the surface area for a hemisphere, which is nothing but half of that of a sphere, right? And also one more thing, if you are considering only a hemisphere which is having a flat base, if you are only considering a hemisphere which is having a flat base, so at that point you have to add the top surface area as well as the base surface area, right?